Good afternoon, everyone. Sorry about the hiccup, but I try to be quick. But we felt it is kind of a good opportunity after seeing all these presentations today that we give you a quick summary of the techniques that we have developed over the years at University of Bristol and how we make use of them to connect to the studies we do. So this is what we are seeing. We have presented a propeller research in turbulent streams, no axial flow, distributed ducted configurations, as well as numerical studies. And these are just some of the selected topics that we do at Bristol. We actually do extend further beyond these topics. And for instance, tandem rotors that Marty has mentioned, and also we investigate quite a lot into noise suppression, noise mitigation methods. And to do this, we are mostly interested in two aspects. One, aeroacoustic characterization, and second, why are these noise generated? So their generation mechanisms. And to study them, we normally use advanced techniques in experiments, analytically, as well as numerically. And to feedback, because we have so many complex problems, we always basically under the development or in developing advanced techniques as well, which are most suitable for us to understand the problem. So earlier, Marty showed that these are the three main categories of activities we do or techniques we use to study the problem. I would like to just focus on the experimental side because that's the heavy side of the things that we mainly perform at Bristol. Okay, so as we know, propeller is a complex system, so we actually have to we are interested in a range of kind of informations coming out from this type of studies. First of all, we are interested in propeller positions, so we like to synchronize both the propeller and the results of the measurements we do. And then we are interested in aerodynamics, meaning that the thrust and torque. We're interested in the near field and far field pressure fluctuations, flow fields, and lastly but not least, the blade surface information, so blade level informations. So all these require different techniques to achieve it. And we center our techniques, we focus our techniques in terms of synchronized acquisition, meaning that everything, the measurements and the propeller positions are all synchronized so that we can essentially have information across a period of rotation or many periods of rotations. So for instance, the position, far field acoustics, phase. So all these results we have seen from the previous presentations. Propeller torque, force, steady, unsteady wall pressures in installed cases, as well as hot wire MPIV, which basically review the flow field information, and they are also synchronized. So based on one rotation, we are able to see the evolution of the vortex or evolution of certain flow features of interest. What I'm going to do next in the next few slides is that I'm going to highlight the key capabilities of these experimental techniques we used, just to supplement with a bit of further information. So in terms of far field acoustic measurements, we have more than 100 microphones, which are usually fitted in the polar array. And this is the largest set of kind of microphone that you can find in any of the UK facilities. So we do serious acoustic measurements and directivity pattern analysis. And to just highlight some of them, so we have a few independent data acquisition based on national instruments, and each of them is able to have 128 simultaneous channels for microphone measurements, and they can be sampled up to 92 kilohertz. So basically sufficiently high to capture the frequency range of interest. And lastly, they are usually arranged in multiple polar arcs or polar microphone arrays to quantify the directivity in overhead, side, and azimuthal angles. I'm calling it because this is the convention that we follow in the acoustic tunnel, but essentially just the the polar angles of them. And from here, we are able to obtain noise spectra in frequency domain, overall sound pressure levels, variations according to different parameter of interest, advanced ratio, for instance, and lastly, the directivity pattern for all the problems that we study. And secondly, we also have a beamforming array. Beamforming array, different from to the direct microphone measurement, it basically tells us the noise locations. And it usually is useful for installed case again. So if there's any noise components, or if there's any airframe propeller interaction, then we are interested in finding out where exactly does the airframe produce noise. Then we make use of a beamforming array type of studies, where at Bristol, we actually spent, this is one of my pet topic. Anyway, so at Bristol, we have spent quite a fair bit of time in developing the techniques in-house. For instance, here on top of the slides is an 83 reconfigurable beamforming array, meaning that the microphones can be connected and disconnected in locations where we designed them to be. And also, it's elliptic information because we want to capture low frequency, which is also important when it comes to noise understanding. And the code has been written fully in MATLAB in-house so that we can include all different type of post-processing techniques, delay sum, source power integration, deconvolutional methods, as well as time domain methods. And speaking about propeller, this is one of the key kind of design or enabling type activities we do, that we need to design the propeller setup and obtain accurate aerodynamic measurements. So as you have seen from Noah's or Ismail's and many others' presentation, we have quite a rich knowledge in terms of experimental design. And when we design our propeller setup, we design it as a system, meaning that we have all the onboard components in consideration, including the encoders, the motor speed controllers, the load cells, as well as the tachometer, basically quantify the RPM. And we also want to incorporate onboard system which will facilitate our measurements. For instance, the RPM control, meaning that we do have a in-house written code in LabVIEW that enable us to control individual propeller up to 0.1 plus minus % of RPM deviation, meaning that it's really accurate. And also it allows us, as Barack was saying, allows us to do a rotor-rotor phase control within about approximately 1 degree. So all these have been taken into consideration when we are designing our various rigs, and it allows us to obtain the aerodynamic measurements and being validated across the different propeller designs. Lastly, I'd like to just mention quickly that, as you've seen from the earlier nacelles, we also have some kind of experiences with temperature control. So we do incorporate different cooling systems in our rigs, depending on how large the rig is or how large our motor is. And this will enable us to kind of monitor the thermal drift of the load cell. So our aerodynamic measurement is accurate, as well as it helps us to maintain the temperature of the motor so that we can measure, we can do hot wire measurements later, which usually takes a long time. Right. Okay, so for flow field, mainly two asanas. So one is the hot wire anemometry, meaning that we have a few independent hot wire, so constant temperature anemometry systems in-house. And we are equipped with all different types of probes, single to measure total velocity, and dual component to measure U and V velocity components. And it comes in different configurations, straight, boundary layers, 90-degree bends, so that it allows us to access to areas where different access requirement is needed. And from hot wire measurements, we are able to basically obtain velocity spectrals, contours, as well as basically phase logs with the propeller position, so tracking of flow features. And it can also be synchronized with multiple hot wire probes to provide us with correlation studies. And it can also synchronize with other type of measurements, for instance, far field microphone. So we can do some far field, near field correlation studies. So this is, again, in complementary, or I wouldn't say complementary. So another type of flow measurements that we do is particle image velocimetry. This is relatively newer as compared to hot wire probe, because we started to doing this since 2 years ago, maybe. And then for the system, we have a fully time resolved system, meaning that it is able to resolve up to 20,000 kilohertz. But this comes with a compromise, of course, with the field of view because of usually memory requirements. And we have a PIV configuration which can be configured both in planar, so 2D, two-dimensional, or stereoscopic, meaning that 3D. So it gives us all three velocity components in one measurement, and it can be synchronized with basically through our programmable timer unit. It can be synchronized with the blade phase information again, and all these are done with the team, which took some time to develop our communication box and resistance matching techniques, so that the phase locking shows a very robust or very effective position every time when we measure, do the PIV measurements. So basically, we are able to have probably less than 0.5 degree of deviations each time when we lock the phase. Lastly, this is the more about install cases, more about in situ sensors, where we have mainly used it in airfoil studies or in black bodies, where we embed these small pressure transducers. They come from NOW's, Panasonic, or Coolite in case that we are interested in very high frequency information. And they can be configured in situ and remote configuration, meaning that they can be either embedded there or they can be connected through a tube, which is the second peak over there on top. And then the pressure, unsteady pressure fluctuations information will be collected through there. And normally the frequency response is pretty good, up to 10,000 hertz and up to 3,300 kilohertz for Coolite, which Hakan has used before. And this is mainly for us to be interested or to get information out from airframes, again, aeropropulsive interaction type of studies, where we want to understand where exactly or which part of the pressure is important. And this whole system of so-called in situ sensors are also paired in-house development with the National Instrument Data Acquisition System. So essentially, they can be measured together and simultaneously with the far field too. So what's next? Or as we have seen from the previous presentations, there's a need in terms of blade level instrumentation or blade level information. For instance, it will help us to optimize propellers from a noise perspective, or it will help us to essentially understand how important is laminar separation bubble, for instance, in terms of noise generation. So all these will have to come from blade level information. And this is what we are developing. And some of them have already begun for some time. And some are in the development phase where we have already secured grants for. The first one is basically to determine the pressure and skin friction coefficient on the surface of the blade through oil film interferometry. And secondly, we are developing mini transducers, which will be essentially embedded onto the blade. So similar to larger scale airfoils, we want to extract unsteady wall pressure fluctuations from the blade itself and list these very nicely to our ongoing, I should say, ongoing endeavors about National Propeller Testbed, which Marty will talk a little bit more about in the afternoon. So that's a brief summary of all the experimental capabilities we have, and thank you.